more definitions here. So we're starting by looking at connected graphs. And what is a connected graph? Well, every vertex in the graph can be reached from every other vertex in the graph. And basically, we are not taking our pencil off the network. If we have to take our pencil off to get to another vertex, then it is not connected. So remember, it can go via another vertex. So let's have a look at graph A to start off with. If I wanted to go from A, can I go to every other vertex there? Yep, I can go straight to B, I can go to C, I can go to D, and no matter what vertex I start at, so if I started at C, can I get to B, A and D? So yes, that is a connected graph. Same thing for the next one. I can go from A right down to B. Yes, I have to go through C and D, but that's okay. I don't take my pencil off the network or the graph in order to get there, so therefore it is connected. And the last one. Here, if I wanted to go from A to B, can I? Yes, I can. I can't go directly, but I can get there without taking my pencil off the paper, and so that is why that is connected. Here's an example, a couple of examples of ones that are not connected. So looking at graph 1 there, you can see in order to get to B, I would have to take my pencil off the graph. So if I was at C, I can't get to B without lifting my pencil, and therefore that is not connected. Not connected. Same thing with graph 2. D is out there on its own, and so therefore I cannot get to it without lifting my pencil. If I wanted to get to B from A in the next one, I'd have to take my pencil off the vertex here to get to that vertex at B, and therefore it is not connected. So basically, if they're not joined in any way, and that's all the vertices in the graph, then we consider them to be not connected. Another term that we need to be familiar with is a bridge. Now, a bridge only exists in a connected graph, so the graph must be connected to start off with. And then if there is an edge that we can remove that makes the graph disconnected, then that edge is considered to be a bridge. So if you have a look here, if I took away this edge between C and D, so edge CD, then that graph would become disconnected. So CD is a bridge. Now, information from a graph can be put into a matrix, and we call them adjacency matrices. We can go from a matrix back to a graph, so we should be able to move both ways. So let's have a look here at this graph. The adjacency matrix records the number of edges connecting each pair of vertices in the graph. So that's what we're going to do when we put together our adjacency matrix. It's always going to be a square matrix. Now, if you recall, what a square matrix is from matrices is when the rows and columns are the same. So here, because we have 4 vertices, A, B, C and D, that'll go up the top and it goes down the side as well. So it's a 4 by 4 matrix. So let's start. How many edges are there that connect A to A? And hopefully for you, the answer is 0. How many edges are there that connect A to B? Can you see it? There are 1. A to C, again, there is 1. And A to D, there are 2. Okay, so you've got 1 and 2 there. Let's do the next row. We are going B to A. Well, we've already done A to B, so it should exactly be the same number. And next one, B to B, well, it's not a loop or anything, so it is just a 0. B to C, there is one edge, and B to D, there are no edges. You cannot go directly there. Next one, C to A, 1. C to B, 1. C to C, 1. C to D, 0. Last row, all of these have been done before. So D to A we know is 2. D to B is 0, and the rest are 0 as well. Now one thing that I want you to have a look at there. Now I've just drawn a diagonal, a leading diagonal from the left hand corner down to the right hand corner there. And hopefully you can see that on either side of that line the values are the same and exactly the same position. So they are symmetrical. So we will talk about that a little bit further on. Keep that in mind.